Hi everyone, today we're going to look at Gauss's Law. It's an extension of what we learned with electric flux last class. And we're going to start with we're going to look at electric flux again and see how it leads to this equation Gauss's Law, which lets us calculate electric fields. So first, last time we talked about electric flux. For a uniform electric field through a flat surface, you can calculate electric flux by E dot A. And the way to think about it is we're measuring how much electric field goes through a particular surface. Right? The more electric field lines go through an area, the larger the electric flux is. And it's easy to calculate for a uniform electric field on a flat surface. More generally, it's the integral of E dot dA. It's the surface integral of an electric field through an area. That's if I have a changing electric field in a curved area. This is the most general representation of electric flux. And we saw in particular that if I have a positive charge inside a closed surface, so an integral over a closed surface is represented with this little circle around the integral here. In that case, the electric field, the flux of the charge through each surface is going to be positive because this is a positive charge, so the electric field lines are all going away from it. And as they go through the air, as they cross the surface, they're going outwards, and the area vector is pointing out from, by definition, the area vector points out of the closed surface. And you see the angle between the area vector and the electric field is always going to be less than 90 degrees. It means you're always going to have a positive flux. So we get a net positive flux when the charge inside it is positive. And when the charge is negative, you sort of get the opposite. We get a net negative flux. And once again, that's because the electric field lines are all pointing inwards and the area vector is all pointing outwards. So the angle between the area and the electric field is going to be greater than 90 degrees, which when you do the cosine of the angle gives you a negative number. So when the total flux is negative, the charge inside is negative. And when the charge is outside, in this case, every electric field line that enters also exits. Every electric field line that enters also exits. And you get overall, that all the negative flux from when it enters is canceled out by the positive flux when it exits. And so the net flux when there's no charge inside it is 0. So the amount of electric flux through a closed surface is directly proportional to how much charge is enclosed. And that leads to our statement of Gauss's law. Here it is, the first of Maxwell's equations. Maxwell's equations is a set of 4 equations that describe electric and magnetic fields and the relationships between them. And here's the first one. It's what we were just saying. The electric flux is equal to Q enclosed, or is proportional to Q enclosed. And the proportionality constant is this epsilon naught. So the integral of E dot dA over some closed surface will be equal to how much charge is enclosed. And we can use this to calculate electric fields. And we're going to see all the different ways that we can calculate electric fields using this for certain particular symmetric situations. So let's look at some simple examples here. I have 5 situations where I have charge inside a Gaussian surface. So 4 of the Gaussian surfaces are spheres and one of them is like a cube. And it asks rank in order from largest to smallest the electric flux through each of the surfaces. So remember, the electric flux is just this thing here. This is Gauss's law. It's the integral of E dot dA, that's the electric flux. And the electric flux is just directly proportional to Q enclosed. So the more enclosed charge, the larger the electric flux. The shape of these things doesn't matter. So the fact that this one has a radius r, this one has a radius 2r, the total electric flux through them will be the same if they have the same charge. So look at this one. The electric flux to this one is just going to be the enclosed charge divided by epsilon naught. So this one here, it'll be Q over epsilon naught. For the second one, the charge is 2Q, so it'll be 2Q over epsilon naught. For the third one, also Q over epsilon naught. For the next one, also Q over epsilon naught. For the last one, it's 2Q over epsilon naught. So 2 of them have a flux of 2Q over epsilon naught, and 3 of them have a flux of Q over epsilon naught. And that leads to this ranking here, right? B and E are the largest, and then A, C, and D are the next largest. Same with here. Rank them from largest to smallest flux. Well, these 2 have the same flux. That's supposed to be an arrow. Can you believe that? They have the same flux of Q over epsilon naught. This one, Q enclosed is 0. There is no charge inside it. That 4Q next to it does not contribute to the net flux. So the total charge inside that one will be 0. The total flux and charge of this one will be 0. This one will be 3Q over epsilon naught. So C is the largest because it has the most enclosed charge, then A and B. And then D is going to be the least because it has no enclosed charge. Okay, so let's use Gauss's law to calculate some electric fields for very specific situations. Here's Gauss's law again, right? The integral of the electric field over the area, that's the flux, is equal to Q enclosed over epsilon naught. And we're going to use this to find some electric fields for some very specific situations. We'll pick a Gaussian surface, the thing that we're going to integrate over. We're going to find how much charge is inside the Gaussian surface, then we're going to solve Gauss's law. Pretty straightforward. So the first case we want to do is for a point charge. We've already seen what the electric field for a point charge is, and remember the electric field for a point charge is 1 over 4 pi epsilon naught Q over r squared, right? That's the magnitude of the electric field. And we're going to see if we can get the same thing here using Gauss's law. So let's pick a Gaussian surface for this. Now, when you're picking Gaussian surfaces, you pick something that is helpful for the particular situation. We know that for a point charge, the electric field is spherically symmetric, so a sphere is often the best case. So I have a spherically symmetric electric field, so I'm going to pick a sphere to represent as my Gaussian surface. So there's my sphere for my Gaussian surface. And if I were to look at the electric field created, say, right here, a distance r from here on the sphere, so it's a sphere of radius r. What's the electric field that it's going to create here? Well, the electric field that it's going to create is going to be in that direction, right? There'll be an electric field pointing radially away from the charge. What's going to be the area vector? Well, the area vector at any point on a sphere is going to be perpendicular to the surface. It's going to be pointing away like that. So we see there that it's pointing directly away. Same as if I were to pick, say, here, right, as my radius. The electric field would be pointing radially away like this. And the area vector would be pointing in the same direction, right? dA. And that would be the same at any point along there. And what's nice about this is in the equation, you know, we have that E dot dA shows up in the equation. And that's just the magnitude of E times the magnitude of dA times the cosine of the angle between them. They're pointing in the same direction, so that's cosine of 0, and that's equal to 1. So then this dot product is going to be E dot EDA, which is going to make things a little bit easier. The other thing we need for this is Q enclosed. So how much charge is enclosed inside this Gaussian surface? Well, if you look, all the charge is inside my Gaussian surface. Let me label this my Gaussian surface. All the charge is inside the Gaussian surface, so the Q enclosed is just plus Q. So now we have everything we need. We can apply Gauss's law and get our result. Gauss's law. So first thing you should do is always write down Gauss's law. So it's the integral of E dot dA is equal to Q enclosed over epsilon naught. And I'm going to replace that E dot dA with what we figured out. It's the integral of E times dA, because that cosine of 0 becomes 1. And the enclosed charge is just Q. Now the next step is that the E is constant. This is a constant value at every point along the sphere, everywhere around the sphere. At any point the electric field is the same anywhere. So I can pull it out of the equation. So I'm going to pull this out and make it like this. I end up with the integral of dA, and with the E on the outside, Q over epsilon naught. So this here is just the integral over a sphere is just going to be equal to the area of the sphere. It's the integral dA, so it's just going to be equal to the area of the sphere, right? And the area of the sphere is 4 pi r squared. So this becomes here this becomes E times 4 pi r squared is equal to Q over epsilon naught. Solve that for E. I'm going to move things over. E is equal to 1 over 4 pi epsilon naught Q over r squared. And we have now our electric field due to a point charge. Nice and easy. And this result is the same as what we saw before, right? Just kq over r squared. So let's apply it for another spherically symmetric situation. We're going to try it for a thin spherical shell, or a ping pong ball, right? A thin spherical shell. So here it's a charged thin spherical shell. So we see here that the charge is all on the outside of the sphere. Total charge Q, the sphere has a radius r. And what we're going to do here is we're going to calculate the electric field both inside and outside. So let's do it outside first, because that's going to be familiar. All right, so I want to calculate the electric field outside, so I'm going to draw a Gaussian surface outside like this. So this is my Gaussian. I'm just going to say Gaussian because we don't have time to say Gaussian surface every time when we're outside the sphere. So here, at this point here, it has radius little r, and I'm assuming it's spherically symmetric, right? So I'm assuming that at this point the electric field is pointing that way, and that the area vector is also pointing that way. So when you go to do the E dot dA, right, that just becomes E times dA, just like before, because they're parallel and the angle between them is 0. Let's do it for, let's calculate then for r less than, for r less than, no, greater than capital R. So this is outside the sphere, right? So here's outside the ping pong ball. So how much charge is enclosed? What is Q enclosed in this case? Well, I drew my Gaussian surface outside the ping pong ball. Here's the ping pong ball, or the charged sphere, and the Gaussian is outside it, so all the charge is enclosed. So Q enclosed is just going to be plus Q. So now I write down Gauss's law, right? It's the integral of the electric field dot dA is equal to Q enclosed over epsilon naught. And once again, this becomes the integral of EdA is equal to Q enclosed is just Q. I can pull out that E, and I end up with the integral dA like before. So this actually ends up looking a lot like what we had before. I'm going to put in for the area. So the area of a sphere is 4 pi r squared. And I solve for E, and I get the exact same answer that we did for a point charge. And that's actually kind of an important result. This is saying that the electric field outside a spherically symmetric charge is the same as if it were a point charge. So when we're outside that sphere, it behaves exactly the same. So let me write that down. This behaves exactly the same as a point charge when we're outside the sphere. Point charge. And that's good to know. Now let's look inside. I want to calculate the electric field inside this thing. So we know that everywhere outside it's just spherically symmetrically pointing that way like that. But inside I want to calculate it. So we're going to assume that it's spherically symmetric. So here's my, let me draw that a little more clearly. Here's my Gaussian surface. This is my Gaussian for inside. This is my Gaussian, which I wrote with 3 S's for some reason, inside the sphere. So let's say I have, here's my radius r. I'm going to assume that the electric field is pointing in the same direction as the area vector as before, right? And so let's get started with that. So inside the sphere. So the big difference here is, what's the enclosed charge? The enclosed charge inside the sphere, right? How much is inside this surface? Well, none of it. All the charge is out here, outside that purple Gaussian surface. So I'm really upset that I didn't do this in purple. Q enclosed is going to be 0 because there's no charge inside there. So that is going to make our derivation much easier. Equals, you write down Gauss's law, Q enclosed over epsilon naught, and this here, just like before, is going to lead to E times 4 pi r squared, and Q enclosed is 0. So that leads to an electric field equal to 0. So inside the sphere, the electric field is 0. Let's think about that. Right at the middle of the sphere, right here at the tip of the lightsaber, we expect it to be 0. The electric field created by here is going to be canceled out by the electric field by there. The electric field here is going to be canceled out by the electric field there. So by symmetry, it's going to be 0 here. But if I go over here, I'm a little closer to these guys. So these guys are going to create electric field pointing to the left, but then there's all this charge over here that's going to cancel it out. So everywhere inside this sphere, if you were to add them all up individually, you could show that the electric field everywhere inside here is 0, which is kind of an interesting result. One way to think about it is to draw a graph showing that. So if I were to draw a graph of electric field versus distance, right? And I were to make maybe this would be at the radius r where you exit the sphere. When you're outside the sphere, it behaves just like a regular 1 over r squared, right? Outside the sphere, we saw that it just goes, the electric field goes off here. The electric field is just 1 over 4 pi epsilon naught q over r squared. So it goes off as 1 over r squared. But when we're inside, the electric field is 0. So here the electric field is 0. Then outside it goes off as 1 over r squared. So that's the electric field for a shell. This next example is for a long line of charge. So if we have a line here, it's very, very, very long, and it has charge on it, positive charges distributed on it, and it has linear charge density lambda. So linear charge density lambda is just how much charge it has per unit length. So if lambda is, if lambda is 6 coulombs per meter, then every meter of the line has 6 coulombs of charge. And the electric field that this is going to create is going to be pointing away, right? At any point here, it'll be pointing away from the line here. It'll be pointing away from the line here. It'll be pointing away from there. This is going to be a cylindrically symmetric electric field. So what I'd like to do is choose a Gaussian surface for this one that is a cylinder. So there's my Gaussian surface right here. This is my Gaussian surface. I'll call it here Gaussian. All right, and we're going to use that to calculate the electric field due to a long line of charge. And remember, this here is the linear charge density. Linear charge density. So let's think about the electric field at any point. If the electric field here, remember this is going to be a cylinder of radius r and length, we'll say L. So the electric field at that blue point there is going to be pointing in this direction. There's my electric field. And the area vector is going to be pointing also in that direction because it'll be perpendicular to the surface at every point, right? So in this case here, E dot dA is just going to be like before. It's going to be E times dA. Now let's look at a point here along the top surface. So at the top, right, this area here is the top surface, and at the top the electric field is still pointing away, right, here, but the area vector is pointing upwards. right? So on the outer surface over here, the electric field is pointing in the same direction as the area. But here on that top surface, the electric field is still pointing away from the line, but the area vector is pointing straight upwards. So that means these are perpendicular, which means that when we take the dot product of those two things, right, it's going to be 0, because E dot dA is going to be equal to E times dA times the cosine of 90 degrees, which is 0. So there it's going to be 0. And same for the bottom. If you look at the bottom surface here, the electric field here is pointing to the right on the bottom surface, and the area vector is pointing downwards, right? So this flux is also going to be equal to 0. So here, E dot dA is also going to be equal to 0. Okay, so for all three surfaces, we have three surfaces to deal with. We have this outer wall, we have the top, and we have the bottom. And we have everything we need. We need, oh, I lied. We need one more thing. We need to find Q enclosed. So Q enclosed is how much charge is inside it. So let's see, we need the charge from here to here, right? Along the line that is inside our Gaussian surface. This has a length of L, and the amount of charge per unit length is lambda. So Q enclosed will be lambda, charge per unit length, times L. So keep in mind that, remember, this here is coulombs per meter, and this here is in meters. So when you multiply them together, you're going to get the amount of charge that is inside that particular one. So we have Q enclosed, so now we have everything we need to calculate the electric flux, or the electric field at any point. So here's how we do it. We start by writing down Gauss's law. So I write down E dot dA is equal to Q enclosed over epsilon naught. That's Gauss's law. So I'm going to write it down now for the three different areas. There's the top, the bottom, and the wall, right? So I'm going to do the integral of the electric field dot dA for the top little circle. There's that circle at the top, plus the integral of E dot dA for the bottom, plus the integral of E dot dA for the wall. And that's going to be equal to Q enclosed, which is lambda over epsilon naught. And as we saw, this one is 0 and this one is 0, because in both cases the electric field is perpendicular to the area vector, which means the dot product is going to be 0. And so we're just left with the electric field due to the wall. And so at every point along the wall, the electric field is the same, because every point on the wall here is a distance r from the wire. So the magnitude of the electric field is going to be the same at every point. So we end up with the integral of E dA equals lambda L over epsilon naught, or E integral dA, so this is for the wall, equals lambda L over epsilon naught. So what's the area of that wall? Well, the area of any cylinder is the circumference times the height. So the circumference is 2 pi r times the height, which in this case is L, is equal to lambda L over epsilon naught. You notice that the L's cancel in this case. That's important, because this is a really, really long line of charge, right? It's infinitely long. And we just picked a cylinder of length L to help us calculate the electric field. But this cylinder is not a real object. It's just, this cylinder is just a surface to help us calculate it. So the length of the cylinder should not matter, because it's not really part of the actual physical setup. So the L's cancel out. When I solve for E, I end up with E equals 1 over 2 pi epsilon naught lambda over r, which is what we saw before when we calculated. So this is similar to the result we got before. Next, I'd like to apply Gauss's law to another symmetric situation, a very large sheet of charge. So let's assume this is a sheet in the xz plane, and it's infinitely large, and it has surface charge density sigma, right? Surface charge density sigma. And I want to, we know what the electric field looks like for this. Above the sheet, it's pointing upwards in the plus y direction. Below the sheet, it's pointing downwards. So I'm going to pick a Gaussian surface, and you'll see why I picked this one in a moment. So I'm going to pick a Gaussian surface that's actually a cylinder. So above the surface, it's like this, and then it hits the surface right here, and then it continues below the surface like this. Okay, so this is going to be my Gaussian. Let me make my pen a little finer, and it's going to have, you know, a radius r and a length l, like so. So now, with this Gaussian, we can look here. Let's say if I look at a point on the top, at the point on the top, the electric field points upwards, right? And the area vector also points upwards. So in this case, the E dot dA, right, is going to be just E times dA. So E dot dA, because they're pointing in the same direction, that just becomes E dA. But if I look at the electric field above the surface here on this wall, the electric field is still pointing in that direction, and the area vector on the wall is pointing outwards, right? So in this case here, E dot dA is going to be 0 because they're perpendicular to each other. And it's the same in the bottom, right? If I look at the bottom, my electric field is pointing that way, and dA is pointing the same way, so that one is not going to be 0. So I have everything I need here. Oh, I almost have everything I need. I also need the enclosed charge. So here is the amount of charge enclosed inside the surface, right? So how much is that? Well, Q enclosed is just going to be the surface charge density times the area of that surface that's enclosed inside there. So the surface charge density is going to be sigma, and then the area is just going to be pi r squared, because we picked a cylinder of radius r. So now we are good to go, and I think we can calculate our electric field. Let's write down Gauss's law as we always do. Integral d dot dA equals Q enclosed over epsilon naught. And integral E dot dA is going to give us 3 areas again. So it's going to be the integral of, oh, that's over the whole thing, but here it's the integral of E dot dA for the top plus the integral of E dot dA for the bottom plus the integral of E dot dA for the wall is equal to Q enclosed, which is sigma pi r squared over epsilon naught. And as we saw in this case, for the wall, E and dA are perpendicular. So here, because they're perpendicular, the wall goes away. But for the top and the bottom, the electric field is constant everywhere on the top, so we're just going to do E times the integral dA for the top plus E times the integral dA for the bottom is equal to sigma pi r squared over epsilon naught. And the area of the top is the same as the area of the bottom. It's going to be pi r squared. It's the area of a circle. Now, look at all those pi r squares. Let's cancel them all. Both sides of the equation. So on the left side, we just end up with 2E equals sigma over epsilon naught, or the electric field is equal to sigma over 2 epsilon naught. And that is the electric field for a large surface that we got with our really unpleasant integral before. It's uniform throughout all space, and it's either pointing straight up or straight down, and it's just the surface charge density divided by 2 epsilon naught. Here's one more example. This is a fun one. What if I have an insulating sphere with uniformly distributed charge? So the sphere has total charge Q, and the charge is not just on the surface, it's everywhere throughout the whole sphere, and it's uniform. Calculating the electric field inside and outside. So calculating it outside is actually pretty easy. It's similar to what we did before. So if I were to draw a Gaussian surface outside, right? So here's the Gaussian for R. This is just like with the ping pong ball. So this is the Gaussian for R greater when we're outside the sphere. And for R greater than R, you know, the Q enclosed is all of it, and the Gaussian, you know, I'll skip the steps, but if you look at the examples we did before, right, you end up with E times 4 pi r squared, and Q enclosed is Q over epsilon naught. Skip some steps and then solve, and you get that the electric field is 1 over 4 pi epsilon naught Q over r squared. So that one's easy. That's just outside a spherically symmetric situation. You have the same electric field as you would otherwise. But now, when we want to look at inside, it's a little bit trickier, because if I want to look at inside, so here's my Gaussian for R inside. Here's this is the Gaussian here for R less than R. That's a little bit trickier, because Q enclosed, we're only enclosing a fraction of it, right? When we're outside, we're enclosing all the charge Q, but here we're only enclosing some of it. And so the way you would calculate the enclosed charge, you can try to think about it and pause it and figure it out for yourself if you can, but I'll show you my resolution. It's a fraction of the total charge, and the way you can do it is you can do the enclosed, not area, but the enclosed volume by the sphere divided by the total volume, right? That fraction will give you how much of the charge is enclosed. So it'll be Q, so the enclosed volume would be, the volume of a sphere of radius little r would be 4/3 pi r cubed, but the total volume of the whole sphere is 4/3 pi capital R cubed. So Q enclosed here is just going to be Q, we see a lot of canceling out there, R over R cubed. So now, using this, we can write down Gauss's law and figure it out. So Gauss's law, here, I'm going to move this here so that we can have some room. So Gauss's law is the integral of the electric field dA equals Q enclosed over epsilon naught. So this becomes E times the area. I'll skip some of the steps. I can skip it here because I'm special, but on the exam I want you to write those extra steps. 4 pi r squared, right, because the electric field is constant everywhere along the surface. The area vector is parallel to that, so it's just E times A, and the area is 4 pi r squared. Q enclosed is now Q r over r cubed over epsilon naught. So if I rewrite this, you notice that that r squared cancels out, only cancels out 2 of the r's on the right hand side, and so we end up with E equals 1 over 4 pi epsilon naught Q over r, big R cubed, and then we have an R. So the electric field outside is 1 over 4 pi epsilon naught Q over R cubed, that's all constant, times R. So, sorry, that's inside, right? We're inside the sphere. So the electric field gets stronger as you get further and further out. At R equals 0, it's 0, and then it increases. It gets larger and larger and larger until it reaches the surface. Then it switches to this, where it goes off as 1 over R squared. So the best way to see that is to draw a graph again of the electric field versus the distance. And here I will put R, right? So when we're outside, it just goes off as 1 over R squared again. So when we're outside, we saw that it does this thing here. Right, it's just a 1 over R squared. That's from this. Now, when we're inside, we're going to use this equation, and you see that it's a linear equation. It increases linearly as R. Right, so inside the sphere, the electric field, inside the sphere, where's my little pointer? Inside the sphere, the electric field increases as you're enclosing more and more charge. Then, once I get to the surface of the sphere, the electric field starts to get weaker as I get further away from the charge. Neat.